Hello everyone. So this is the second hour of waves, and in this hour we are going to talk about velocity of string wave, velocity of sound wave, and about the standing waves. So without wasting time, let's start learning the velocity of string wave. So speed of string wave. If we have a wave on a string, then the speed of the wave is given by under root of t by mu. What is t? The tension in the string. And what is mu? The mass per unit length of the material used to make the string. Here, I would like to talk about that if you have a string of, let's say, made up of material of density rho, having a cross-sectional area A and having a length L, then what will be the relationship between mass per unit length and mass per unit volume, which is density? So mass per unit length means that the mass of this whole string divided by its length. So that will be equals to m by L. While the mass per unit volume is the mass of the string divided by its volume, and the volume of this string will be cross-sectional area into length. Now, in place of mass per unit length, here you can substitute mu, which is the mass per unit length. So you can say density is nothing but mass per unit length upon cross-sectional area, or you can write mass per unit length to be density times the cross-sectional area. So here V is the speed of the string wave, T is the tension in the string, and mu is the mass per unit length of the string. So if the string has a mass m and a length L, then the mass per unit length is nothing but mass divided by the length. Now, question is, the speed of wave on a string depends upon the amplitude, if you create a pulse of large amplitude, or you create a pulse of lower amplitude, or does it depend upon the frequency of source? So the speed of wave on string depends upon the amplitude of wave, the frequency, both of them, or none of them. Now see, we know that the formula for speed of a wave on string is given by under root of t by mu. Yes sir. What is t? Tension in the string. What is mu? Mass per unit length of the string. Does the speed depends upon amplitude? No. Does the speed depends upon frequency? No. So it depends upon what? On two things, the tension in the string and the mass per unit length. So the speed of the wave on a string V equals to under root of t by mu. Here T is the tension in a string and mu is the mass per unit length. The speed of the wave on a string is independent of both frequency and the amplitude of the wave. So keep this thing in mind. So what does the speed of the wave on a string depend upon? Tension in the string, mass per unit length of the string. The speed of a wave in a medium depends upon the property of medium. Keep this thing in mind. I will elaborate more on this. Repeating once more, the speed of a wave in a medium depends upon the property of medium. So without wasting time, let's see the next question. Question is, there is a string and here we have a block of mass m. The second case, we have the same string, the same block, but this time the block is submerged inside water. Question is, if on immersion of block in water, the speed of the pulse on the string becomes half, the speed becomes half. Find the density of the block material. So first time you will say that, okay, here the tension in the string has to be equals to mg. And since you have immersed it inside water at a later stage, that's why the tension here will be less than mg. Now the question says that if on immersion of block in water, the speed of the pulse on the string becomes half, find the density of the block material. If I tell you that V equals to under root of T by mu, if tension becomes double, speed becomes root 2 times. Tension becomes triple, speed becomes root 3 times. How many times the tension should become for the speed to become half? So sir, how many times the tension should become for the speed to become half? The tension should become 1 by 4 times. When the tension in the string will become 1 by 4 times, you will get outside an extra term of half, and that will make the speed half. So V equals to under root of T by mu. Yes sir. V is proportional to T raised to power of half. Yes sir. For the speed to become half, the tension should become 1/4, and you should be able to guess these things instantly. So for the speed to become half, the tension should become 1/4. For the tension to become 1/4, the effective weight of this block should become 1/4. Now, what is the effective weight of a block suspended inside a fluid? So we know that the weight effective equals to the actual weight into 1 minus the density of fluid upon the density of body. We have learned this in fluids, right? Physics is one big continuum. You need to know everything to score marks. So you can say the velocity apparent should be, which is equals to 1 minus density of fluid upon density of body, should be equal to 1/4 the original weight. Sir, why? Because beta v equals to under root of t by mu. Yes. So for the speed to become half, tension should become 1/4. For tension to become 1/4, the effective weight should be 1/4 the original. Original weight was mg. So now the effective weight has to be equals to mg by 4. So you will say the apparent weight W by 4 equals to the actual weight, say W, which is equal to mg into 1 minus density of surrounding fluid. What is the surrounding fluid? Water. What is the density of water? 1000 kg per meter cube. Do we need to remember this data? Yes. This data won't be provided in your NEET examination. So you should know that the density of water is 1000 upon the density of body. Now beta, both the side, the weight get cancelled. So what you get is 1 by 4 equals to 1 minus 1000 upon density of body. Now you can bring this whole term to the left hand side and this 1 by 4 to the right hand side. So you will get 1000 upon density of body equals to 1 minus 1 by 4, that becomes 3 by 4. 1, bring this 1 by 4 to the right hand side, 1 minus 1 by 4 gives you 3 by 4. Hence, the density of this body has to be equal to 4000 by 3 kg per meter cube. So this will be the density of the body. Easy question, important question. Okay, let's move on and see the next example. Question is, there is a wire of mass m and length l. If the string is suspended under its own weight, determine the speed of a pulse at a distance x above the lower end and what will be the acceleration of the pulse. Okay, so our mission is to find the speed of the pulse at a random distance x above the lower end. We know that the speed of the pulse is equals to under root of t by mu. If we create a pulse at the lower end and let it go up, let it move away from the source, what will be its speed at different point? At the lowest point, we know that the tension will be 0. Yes, sir. And at the highest point, we know that the tension will be equal to the entire weight of this string, that will be mg. If I ask you what will be the velocity of the pulse at the lowest point, so the velocity of the pulse at the lowest point has to be under root of t by mu. So under root of tension in the string 0 upon mu, which is mass per unit length. Since the tension is 0, the velocity at the lowest point is 0. What will be the velocity of pulse on reaching the top? So the velocity of the pulse at topmost point equals to under root of tension at the top. At the topmost point, the tension will be equals to mg upon the mass per unit length, which is m by l. So what we get here is under root of gl. So at lowest point, the tension is 0. At the topmost point, the speed is equals to root gl. Our mission is to find the speed at some intermediate position, at some random distance x. What to do? So you will say, at some random distance x, we can determine what will be the tension in this string. In this string, the tension will be due to the weight of the string below it. The whole string of length L has a mass m. Then what will be the mass of a length x? So the mass of a length x will be equal to total mass upon total length into the length x. Once we know what is the tension at this point, we already know what is the speed. So we can say at a distance x from the lower end, the tension will be equal to the weight of this much part. How much weight? Its mass multiplied by g. And the mass will be equals to m into x by l from unitary method. See better. M by L represents mass per unit length of this wire material, multiplied by the length x whose mass you wish to find, so that you can find the weight of this part and hence you can find the tension here. So you will say the tension will be equals to mx by L into g. This will be the tension. Now what will be the speed? We know that speed has to be equals to under root of t by mu. The tension is mgx by L, and you know that the mass per unit length represented as mu will be m by L. So you will get speed equals to under root of t by mu, which will be mgx by L upon m by L. Cancel out bachcho m. So the speed comes out to be equals to root gx. So at a distance x above the lower end, the speed will be equals to root gx. First part is done. The second part they're asking me in question is, what is the acceleration of this pulse? Why there will be an acceleration? Sir, at lowest point tension is 0, so speed is 0. At highest point, tension is maximum, so speed is maximum. So if you create a pulse at the lower end, as it goes up, the speed of the pulse increases because the tension is increasing. Our mission is to find what is the acceleration, what is the rate of change of this speed with respect to time. So, sir, how to find? See, here you know that v as a function of x. We know that acceleration can be written as dv by dt, yes, but it can also be written as v into dv by dx. So if we know the speed as a function of position, using v dv by dx, we can find out the acceleration. So the acceleration can be found using acceleration equals to v dv by dx. Now focus here, v equals to root gx. Write this root gx as g raised to power of half into x raised to power of half. Why? We'll explain. So you can write the speed as g raised to power of half into x raised to power of half. Root is nothing but raised to power of half. So you can say that dv by dx will be equals to g raised to power of half is constant, take it outside. Differentiation of x raised to power of half will give you half into x raised to power of minus half. Now bachcho, you know what is v. V is g raised to power of half x raised to power of half. You know that dv by dx is g raised to power of half into half x raised to power of minus half. So you know that acceleration is v dv by dx. You simply need to multiply v, which is g raised to power of half x raised to power of half, with dv by dx, which is g raised to power of half into half x raised to power of minus half. So you get g raised to power of half into x raised to power of half. This part is v multiplied by half into g raised to power of half x raised to power of minus half, which is dv by dx. So when you multiply them, this x raised to power of half x raised to power of minus half get cancelled. G raised to power of half into g raised to power of half gives you what? G, and there is a 2 in the denominator. Hence your acceleration comes out to be g by 2 in upward direction. So you need to remember this, that this pulse has an upward acceleration of g by 2. This is a constant acceleration. Somebody might have said, sir, you are such a time waster. Why? You could have just compared this v equals to root gx with v equals to under root of u square plus 2ax. The initial velocity is 0, and this part 2ax is same as gx. So if 2ax equals to gx, so acceleration has to be g by 2. Yeah, you can do it. But before solving this, I did not knew that the acceleration is constant. That's why I used this method, that acceleration equals to v dv by dx. But once I have done this and I know that acceleration is constant, now I could have used this method as well. So just remember that if a pulse is created at the lower end, the pulse goes up with an acceleration in upward direction equals to g by 2. So there is one more question coming up based on this thing. So let's see that question. Question is, you have the same string of mass m, length L suspended under its own weight. Question is, if we create a pulse at the lower end, determine the time taken by pulse to reach the top. So if a pulse is created at the lower end, how much time it will take to reach the top. Now since we know that the pulse goes up with an acceleration equals to g by 2, it's very easy to find out time. How? You will say, since the pulse goes up with an acceleration g by 2 and the initial velocity is 0 because the tension at lowest point is 0. So at the lowest most point, the tension is 0, yes. So the initial velocity has to be 0, yes. And you know that this pulse goes up with an acceleration g by 2. So using the second equation of motion, you can say the overall distance traveled L equals to half into at square. So assuming time taken by the pulse to reach the top to be t, that this pulse goes from the lowest point to the highest point in a time t. Using the second equation of motion, I can write L equals to half into acceleration into t square. Now here you got 2 and a 2, this goes up, multiplies here, you get a 4. So the time comes out to be under root of 4L by g, or you can write this to be equals to 2 times under root of L by g. So all you need to remember is that the pulse goes up with an acceleration equals to g by 2. So let's move on. Now what is the intensity of a string wave? First of all, you need to understand what is the definition of intensity. Intensity is nothing but energy incident or energy transferred per unit area per unit time. Intensity is nothing but energy incident or energy transferred per unit area per unit time. Now since we can write energy transferred per unit time as power, so remember that intensity can also be written as the power transferred per unit area. Now, the formula of intensity and the average power delivered by the string wave both look ugly, but they are very easy to derive once you stick to the basics. So let's say we have got this string where the source does SHM with an equation y equals to a sine omega t. I told you guys in the last hour, whatever the source will do, all the points will do the same thing just after some times. So whatever will be the motion of source, each and every particle on this string will start doing the same motion just after some time. So since the source here is doing SHM, each and every particle on this string eventually will do SHM. It's just depend upon how much time it will take for the disturbance to reach that point. The point which is farther away on the string, it will take greater time for the disturbance to reach that point. So let's say the pulse goes with a speed v. So the length of the string that starts vibrating in a time t is vt. If the disturbance propagates with a speed v and you start vibrating it at time equals to 0, then the length of the string that starts vibrating in a time t will be equals to vt. So all these points up to a length vt will start doing simple harmonic motion, right? Because they follow the source. Now, for simple harmonic motion, we know that the total energy is given by half m into omega square a square. So how do you remember all these things? The idea is linked memory. See better. In SHM, the maximum possible velocity is omega a. The maximum possible kinetic energy equals to maximum possible potential energy equals to the energy of simple harmonic motion. And the maximum possible kinetic energy will be nothing but half into mass into maximum possible speed whole square. So we get half m omega square a square. You need to remember all these things. So now, in a time t, the length of the string that starts vibrating is vt. Yes. How much mass of the string starts vibrating? We can find it. We know that the mass per unit length is mu. So if a length vt starts vibrating, then the mass that starts vibrating will be equals to mass per unit length multiplied by the length that starts vibrating. As we can say that the mass of the string that starts vibrating is nothing but the mass per unit length into the length vt that starts vibrating. Now from our study of SHM, we know that energy associated with SHM is equals to half into mass into omega square a square. The mass that starts vibrating in a time t, because of the oscillation of source, that mass is mu vt. So the energy transferred up to a distance vt in time t will be nothing but energy equals to half into the mass vibrating, which is mu vt, multiplied by omega square a square. Now this energy transferred per unit time will be the power. So if I just bring this time down here, that will be the powers, and this is so easy to remember. So you will say energy per unit time equals to half mu v omega square a square. I have just brought this time down here. So half mu v omega square a square. And the energy per unit time is the power. So the power delivered due to this SHM is nothing but half mu v omega square a square. So do you remember this particular formula? No. What I remember is the derivation. In a time t, the length of string that starts vibrating is vt. So the mass of string that starts vibrating is mu vt. And in SHM, the energy associated with SHM is half m omega square a square. So in place of m, I can write mu vt, and then I can bring the t down. So I get the energy transferred per unit time equals to half mu v omega square a square. Now it's easy. Now once you know that power delivered is this much, how to write the intensity? So better remember that intensity is nothing but energy transmitted per unit area per unit time. Energy per unit time can be written as power, so the intensity can be written as the power delivered upon the area through which it is delivered. So if the area of cross section of this string is taken as A, if the area of cross section of this string is taken as A, in place of mu, the mass per unit length, we can write the mass per unit volume times the cross sectional area, right? So you can say intensity equals to half mu v omega square a square, the power transmitted upon the area. And in place of mu, you can write density into the cross sectional area. So you get half rho a, density of the wire material, into the cross sectional area v omega square a square by a. Cancel out a and a. So the average intensity delivered by the source is nothing but half rho v omega square a square. So this is the formula of average intensity. Students usually do not remember both of them, but I promise you, after listening to this particular section, try it once with your own hand. Then try it once with your own hand. After 3 4 days, it won't take you cumulatively more than 10 minutes, but believe me, you will never do any question wrong based on the power of string and the intensity of it. So, since we have talked about strings, now let's move on towards sound. So, sound waves. Sound wave is longitudinal wave. The propagation of sound can be expressed as variation of position of particles or as the variation of pressure. Just like we say that the propagation of light can be expressed as the variation of electric field vector or the variation of magnetic field vector. So the propagation of sound can be expressed as variation of position of particles or as variation of pressure. Now we can write the propagation of sound in two ways. First, in terms of variation of position. So we can write x equals to a naught sine omega t minus kx, where x is the displacement from the mean position. Or we can write in terms of pressure variation as the pressure variation at a point equals to the pressure amplitude into cos omega t minus kx. Here I have taken the initial phase angle to be 0, that's why no term of phi. Now you might be wondering why at one place I have chosen sine and at other place I have chosen cos. This has been done purposefully. Why? Because here we have taken the trigonometric function as sine and cos, as there is a phase difference of pi by 2 in the variation of position and pressure. When I say that the phase difference of pi by 2, think of a wave. For the particle at mean position, we say that the phase is 0. For the particle at extreme position, we say that the phase is pi by 2. For the particle again at mean, we say the phase is pi. For the particle at negative extreme, we say that the phase is 3 pi by 2 and then 2 pi and so on. When I say that the phase difference is pi by 2, it means that when one is at its mean, the another one is at its extreme. That is the meaning of phase difference of pi by 2. And we know that the phase difference between cos and sine comes out to be pi by 2 because we have learned this already. Cos theta can be written as sine of theta plus pi by 2. Hence, as there is a phase difference of pi by 2 between the pressure variation and the position variation, so we have written one of them as sine and another one as cos. So the place where the pressure variation is maximum, the pressure is maximum displaced from its value, the position variation is 0 and vice versa. The place where the position variation is maximum, the pressure variation is 0. So one of them is at mean, another one is at extreme. That's the meaning of it. You just need to remember this particular statement. This will be useful at a later stage. Now this question gets asked. If light can be expressed both as variation of electric field vector and magnetic field vector, which variation do a human eye detect? So a human eye detects electric field variation and not the magnetic field variation. Similarly, when the sound propagates, it can be expressed as variation of pressure or displacement of particles. Which thing a human ear detects? It detects the pressure variation or the displacement variation. So remember that the human ear detects the pressure variation. So our ear detects the variation of pressure. There is a phase difference of pi by 2 between pressure variation and displacement of particle. The place where the pressure variation is maximum, the displacement is 0, and the place where the displacement of particle is maximum, the pressure variation is 0. You need to keep this thing in mind. So the important points that you need to know about sound. First, the healthy human ear can detect frequency from range 20 Hz to 20 kHz. So 20 Hz is the minimum frequency that a human ear can detect, and 20 kHz, that is 20,000 Hz, is the maximum frequency that a human ear can detect. Next point, frequency less than 20 Hz is called infrasonic. Just like we have got visible light, yes sir, and the light of energy less than visible is called infrared. So the same way, infrasonic, infrared, infrasonic, less than audible sound is called infrasonic. The frequency greater than 20 kilohertz is called ultrasonic. The maximum frequency that our ear can detect is 20 kilohertz. The frequencies higher than them are called ultrasonic. Okay, so the frequency greater than 20 kilohertz are called ultrasonic. Just like visible, Less than visible, infrared. Higher than visible, ultraviolet. So ultraviolet there and ultraviolet here. The speed less than the speed of sound is called subsonic speed. So if the speed of sound in air is 330 meter per second, then the speed less than the speed of sound is called subsonic speed. Less than the speed of sound means subsonic speed. The speed greater than the speed of sound is called supersonic speed. There are fighter jets which move at speed greater than the speed of sound. Such fighter jets are called supersonic fighter jet. They move faster than sound. So the speed greater than the speed of sound is called supersonic. The speed less than the speed of sound is called subsonic. You need to know these small terminology. Now there is a quantity called Mach number. What is Mach number? Mach number is speed of particle upon speed of sound. Speed of the particle upon the speed of the sound. Let's say the speed of sound is 330 meter per second and some object, some particle moves with a speed of 660 meter per second. Then the Mach number for such a particle will be 660, the speed of the particle upon the speed of sound. So Mach number is nothing but the ratio of speed of particle upon the speed of sound. For this particular case, if the particle moves with speed of 660 meter per second, the Mach number will be 2. So if they say that the Mach number 2, it means that double the speed of sound. When they say Mach number is 3, it means that triple the speed of sound. You might have heard of a product called Gillette Mach 3, a razor. Now Gillette Mach 3, the name comes from that this razor works at the speed of 3 times that of sound. So Mach 3. So Mach 3 means 3 times the speed of sound. Okay. So Mach number is nothing but speed of the particle upon the speed of sound. For everyday object that we see, the Mach number is less than 1 because most of the objects we see in everyday life move at a speed less than the speed of sound. Let's move on. Now, how do we write the speed of sound? The formula of speed of sound in solids is given by under root of Young's modulus upon the density of material. So under root of y by rho. What is y? The Young's modulus. What is rho? The density of the material. So speed of sound in solids is given by under root of Young's modulus upon the density of material. How do we write the speed of sound in case of fluids, that is liquids as well as gases? So in case of fluids, we write the speed of sound as under root of bulk modulus upon the density of fluid. What is B? Bulk modulus. What is the formula for bulk modulus? Bulk modulus equals to minus dP upon dV by V. The reciprocal of bulk modulus is compressibility. So velocity in solids is under root of Young's modulus by density. Velocity in fluids is under root of bulk modulus by density. Now, B is the bulk modulus, rho is the density. If any gas follows a polytropic process, PV raised to power of x equals to constant, do you remember what is the bulk modulus for this particular gas? So, if any gas follows polytropic process PV raised to power of x equals to constant, then the bulk modulus is given by xp. I told you guys, remember it as Windows XP. So if any gas follows a polytropic process PV raised to power of x equals to constant, then for such a gas, the bulk modulus is equals to the polytropic coefficient x times p. Now let's talk more about the speed of sound, and here we will talk about the formula given by Sir Isaac Newton and the correction made over it by Laplace. So we can say that the velocity equals to under root of xp by rho. So we can write velocity equals to under root of xp by rho, as xp is the bulk modulus for a gas following a polytropic process PV raised to power of x equals to constant. Yeah, in waves you have to memorize a lot of things, and this is a theoretical topic, but you will get marks for sure if you are good at theory. Without wasting time, let's move on. So Newton's formulas and Laplace correction. So what did Sir Isaac Newton propose and what correction was done by Laplace? So Sir Isaac Newton assumed that the propagation of sound to be an isothermal process. When we talk in the room, does the temperature of the air in the room increases or decreases? Somebody might say it remains constant. As the temperature remains constant, Sir Isaac Newton said that we should visualize the propagation of sound as an isothermal process. Now for an isothermal process, we know that temperature is constant. Yes, sir. Hence we can say that PV equals to constant. Yes. So the polytropic coefficient, the power of V is 1. So as for an isothermal process, the polytropic coefficient is 1. The bulk modulus, which is nothing but the polytropic coefficient times pressure, can be written as 1 times pressure. So he took the bulk modulus of air to be nothing but the atmospheric pressure. So Sir Isaac Newton assumed the propagation of sound to be an isothermal process. Hence he said that the speed of sound in air should be equals to under root of xp by rho. And as the value of x for an isothermal process is 1, he said that this has to be under root of p by rho. Now, that can be also written as under root of RT by M. In place of P by rho, you can write RT by M. The gas constant times the temperature on the Kelvin scale upon the molar mass of the gas to be taken in kg. So this was proposed by Sir Isaac Newton. Now Laplace did a correction. Laplace said that sound propagates at a very high speed. When the sound propagates at a very high speed, there is no time for heat exchange. As there is no time for heat exchange, the propagation of sound should not be treated as an isothermal process. The propagation of sound should be treated as an adiabatic process. So Laplace pointed out, since the propagation of sound is a fast process, there is no time for heat exchange. As there is no time for heat exchange, it should be treated as an adiabatic process. What is the equation for an adiabatic process? We say that PV raised to power of gamma equals to constant. Now, for an adiabatic process, the polytropic coefficient is gamma. Hence, the bulk modulus will be equals to gamma p, and hence the speed will be under root of bulk modulus by density, which will be under root of gamma p by rho. So, for a polytropic coefficient x equals to gamma for the adiabatic process. Hence, we will say the speed equals to under root of gamma p by rho. In place of p by rho, you can substitute RT by m. So, we get V equals to under root of gamma RT by m. So, which correction did Laplace make? Sir Isaac Newton assumed the process of propagation of sound to be isothermal in nature. Laplace pointed out that since it's a fast process, there is no time for heat exchange, and hence it should be treated as an adiabatic process. So now we have learned the Newton's formula and the Laplace correction. Now the speed of sound should be thought of as under root of gamma RT by M. Remember here, M is what? M is the molar mass in kg. So V equals to under root of gamma RT by M. Here M is the molar mass to be taken in kg. When I say that molar mass in kg, what is the meaning of it? We know that the molar mass of helium is 4 gram. Do not substitute here 4. Substitute here 4 into 10 raised to the power of minus 3. You must substitute the mass of 1 mole of helium but in kg. So you should write 4 into 10 raised to the power of minus 3. That's the meaning of substituting molar mass in kg. So now let's see some important points about the propagation of sound. The first, always use V equals to under root of gamma RT by M. Students do this error of using V equals to under root of gamma P by rho. And if they say if the pressure doubles, what happens to the velocity of sound? And they say if the pressure doubles, the velocity of sound becomes root 2 times. But that leads to error many a time. Why? Because usually when the pressure changes, density can also change. And students neglect the effect of change of density. So this is highly recommended just to look at temperature. If the temperature increases, the velocity will increase. If the temperature decreases, the velocity will decrease. Even if they say in the question that the pressure becomes this times, volume becomes dash times, just look what is happening to temperature. If the temperature increases, the velocity will increase. If the temperature decreases, the velocity will decrease. So sir, why are you emphasizing that we should use V equals to under root of gamma RT by M rather than V equals to under root of gamma P by M? For the gas changing its state, here you have got two variables to deal with, the pressure of the gas and the density. While here you have got only one variable to deal with, which is temperature. The gamma of gas, R, and the molar mass remains constant. Hence, it's better to just look at temperature. So just keep these words in your mind. Whenever you have to think of velocity of sound, I will always think of under root of gamma RT by M, and I will just look at what is happening with the temperature exactly. So if comparison is needed, just look at temperature and not pressure and density. This is the point I have stated already. The second point is that speed of sound in a medium depends upon property of medium and not that of source. For solids, I told you that the speed of sound is under root of Young's modulus by rho. Who's Young's modulus? Mediums. Whose density? Mediums. For a fluid, I told that speed equals to under root of bulk modulus by rho. Whose bulk modulus? The materials. Whose density? The materials. It does not depend upon the source. I ask these questions to all the students. When I say A and when I say B, which sound travels faster from my mouth? The answer is both the sound travel at the same speed. Why? Because sir, you are the source. You are just creating sound. But the sound travels in the medium and the speed of sound in the medium depends upon medium. If you change the temperature of the air in the surrounding, if you change the type of gas concentration, the molar mass in the surrounding, then the speed will change. But me being the source can't change the speed of the sound in the medium. It depends solely on the medium. So, the speed of sound in a medium depends upon property of medium and not that of source. I can't control the velocity of sound in the medium without changing the property of medium. Next thing, take the temperature in Kelvin. Already said. Next point. For a mixture, if they said that there is equal molar mixture of H2 gas and helium gas, then use gamma mixture and use molar mass of mixture. So you can even use the formula V equals to under root of gamma RT by M if you have got a mixture of gases. It's just that use the gamma mixture and the molar mass of mixture when you are finding the speed of sound in a mixture of gases. Next thing, in humid climate, due to addition of lighter H2O molecules, the average molar mass decreases. As the average molar mass decreases, so the speed of the wave increases. Sir, why are you saying lighter water molecules? What is our atmosphere made up of? Sir, the number one is N2. Next, O2. What is the molar mass of N2? Sir, 28 gram. What is the molar mass of O2? Sir, 32 gram. Next come our CO2, which is definitely 44 gram, but these two make up most of the part. So let's focus on these two. So these two have got higher molar mass. To the contrary, our H2O has got molar mass of only 18 gram. So if we keep on adding H2O molecules in the atmosphere, tell me the average molar mass will decrease or increase? Sir, when you find the average molar mass, you take the total mass by total number of moles, right? So that is the average molar mass, okay? So when you are finding the average molar mass, the greater will be the concentration of lighter molecules. The lower will be the average molar mass. So listen to this carefully. In humid climate, due to addition of lighter H2O molecule, in humid climate, due to addition of lighter H2O molecules, the average molar mass decreases. So the speed of the wave increases. That's why sound travels faster in humid climate compared to in dry climate. So this question get asked. You have got two places. One is Mumbai. Mumbai is on the coast, usually hot. And then there is our Rajasthan. Rajasthan is usually dry. On one day, at both the places, temperature is 25 degrees centigrade. Where will the sound travel faster? So, sir, temperature is same. Taking the concentration of the atmospheric gas is same. Gamma is same. R is same. But in the humid climate nearby Mumbai, the molar mass will be less because they have got more number of H2O molecule. As there are more number of H2O molecules, the molar mass is less. So the speed of the sound in Mumbai will be higher. That's why Mumbai is a fast city. So moving on, the speed of sound in solids is greater than the speed of sound in liquids and then the speed of sound in gases. So sound travels fastest in solids, then in liquids, and sound travels slowest in gases. You might know that the speed of sound in water is nearly 4 times the speed of sound in air. Definitely the sound doesn't travel in vacuum. Sound is a mechanical wave. So sound travels faster inside solids compared to that of liquid, compared to that of gases. So the speed of sound in solid is greater than liquid, is greater than gases. So these are all the important points that you need to know about sound. Moving on. Now we will talk about reflection and transmission of a wave. What is the meaning of reflection and transmission? Whenever a wave reaches an interface, so what is an interface? A boundary which separates two mediums. So let's say there is a medium 1 and there is a medium 2. Whenever a wave reaches an interface, For the sake of explaining, I'm using light. So let's say when the light wave reaches an interface, some part of the wave gets reflected and some part of the wave gets refracted, right? So whenever a wave reaches the interface, some part of the wave gets reflected and some part of the wave gets refracted, which I am calling here transmission, getting into the second medium. So when our interfaces form, every time the medium changes, the interface is formed. What is interface? The boundary which separates out two medium. So a medium in which the wave travels faster is called rarer medium or denser medium. Sir, I have learned for light, air is rarer than glass. I think that all of you know this, right? So tell me, in a rarer medium, the light travels faster or slower? So, sir, light travels the fastest in vacuum, then in air, and then in glass. And we say that air is rarer than glass. So, remember that inside a rarer medium, the wave travels faster. Inside a rarer medium, the wave travels faster. So, a medium in which the wave travels faster is rarer medium. The medium in which the wave travels faster is the rarer medium. So, question for you, think of solid, liquid, gas. For sound, which one of them is rarer? For sound, which one of them is rarer? So, a medium is said to be rarer when in the medium the wave travels faster. Out of these three, the sound travels fastest inside the solid. As the sound travels fastest inside the solid, solid will be the rarer medium for sound. And gas is the denser medium for sound. Why? Because inside gases, the sound travels slowly. So first thing you should know about the medium, on which basis we call a particular medium to be rarer or denser. A particular medium is said to be rarer if in that medium the wave travels faster. Next thing, whenever a wave reaches the interface, here I am explaining using the string waves. So here you can see there are two strings, one is thin, one is thick. Now let's say these two strings are made up of same material. Let's say both of them are made up of copper. Then can you tell me which string will be rarer medium and which string will be denser medium? So sir, the speed of string wave is given by under root of t by v. As both are connected to each other, the tension in both of them will be same. So the string that will have lower value of mass per unit length, in that string the wave will travel faster. So out of these two, which one will have lower mass per unit length? So definitely the thinner wire will have a lower mass per unit length. As it will have a lower mass per unit length, the wave will travel faster in the thinner wire and the wave will travel slower in the thicker wire. So just remember, what is a rarer medium? The medium in which the wave travels faster is the rarer medium. For these two strings, if they are made of same material, the thinner wire will be rarer. Why? Because in that one the wave will travel faster. So out of these two, the thinner one will be rarer and the thicker one will be denser. Remember one thing, whatever appears dense need not be dense. I have just taken an example of sound, right? So for the same material and same tension, a thinner string is rarer. Why? Because it has got lesser mass per unit length, so the speed of the wave is higher in the thin wire. For sound, air is denser medium than solid. Why? Because sound travels faster inside solid and slowly in air. So for sound, air is denser medium than solid. And the next point, when a wave reaches the interface, when a pulse you have created reaches the interface, some part of the wave gets reflected and some part transmitted. Until unless it is undergoing TIR, about that we will talk in the topic of optics. Right now, when a wave reaches the interface, some part of the wave gets reflected and some part transmitted. Now let's continue learning the reflection and transmission of a wave. When the wave reaches the interface, there can be two cases. The wave might be trying to move from a rarer medium into a denser medium, or the wave might be trying to move from a denser medium to the rarer medium. So let's take these two cases one by one. The case one, when the wave is moving from rarer medium to the denser medium. So here you can see the pulse has been formed on the rarer medium, the thinner string, and the pulse is trying to enter into the denser medium. Whenever the wave reaches the interface, when this pulse reaches the interface, some part of the wave gets reflected and some part gets transmitted. Again, I am repeating, this is a theoretical part, so you need to be very careful about the understanding of theory. Now, when the wave reaches the interface, some part gets reflected and some part gets transmitted. What I want you to understand here is that the transmitted pulse is in the same phase as the incident pulse. This is the incident pulse. This is the transmitted pulse. So the transmitted pulse is in the same phase as the incident pulse. The crest goes into the denser medium as a crest. While when reflected from the interface of a denser medium, the reflected wave undergoes a phase change of pi. It means that what went an incident as a crest got reflected back as a trough. So there can be two cases. The wave moving in the rarer medium trying to enter into the denser medium. When it reaches the interface, some part gets reflected, some part gets transmitted. Now remember that the transmitted pulse is in the same phase as the incident. The crest keeps on moving in the denser medium as a crest. And the reflected pulse, when reflected from a denser medium, undergoes a phase change of pi. So what goes as a crest reflects back as a trough. So the speed of reflected pulse is same as that of incident. Why? Because they are in same medium. And when the wave is in same medium, it must have the same speed because the speed of the wave in the medium depends upon medium. So the speed of reflected pulse is same as the incident as it is in the same medium. In the same medium, the speed is same, right? So you can see here the reflected pulse has the same speed as the incident pulse. Second point, the incident pulse, reflected pulse and transmitted pulse all have the same frequency. The incident pulse, the reflected pulse and the transmitted pulse, all three of them have the same frequency. Who determines the frequency? The source. The source sets the frequency of the wave. Who determines the speed of the wave in the medium? The medium. Since once the pulse has been created, it has been set at a particular frequency. By changing the medium, the frequency do not alter. What I am saying here works in all three type of waves. It works in sound, light as well as string waves. So the incident pulse, the reflected pulse and the transmitted pulse all have the same frequency. The third point, when reflected from the denser medium, if the wave is moving in the rarer and gets reflected from the denser medium, the wave undergoes a phase change of pi. So the reflected wave has a phase difference of pi with the incident phase. What goes as a crest reflects back from the denser medium as a trough. Next point, transmitted pulse is in the same phase as the incident pulse. So the transmitted pulse is in the same phase as the incident pulse. What goes as a crest keep on following in the other medium also as a crest. So now let's talk about the case 2. When the wave is moving into the denser medium and tries to enter into the rarer medium. The thicker wire represents the denser medium here. So when the wave reaches the interface, again some part gets reflected and some part transmitted. Now this is how the reflected and the transmitted pulse look like. Notice that the transmitted pulse is still in the same phase as the incident. What goes and hits as a crest keep on moving in the denser medium as a crest. But there is a change in the reflected pulse. What went as a crest now reflects back as a crest. When reflected from the denser medium, the wave undergoes a phase change of pi, but when reflected from a rarer medium, a thin wire, it do not undergo any phase change. Since the reflected pulse is in the same medium as the incident pulse, the reflected pulse has the same speed as the incident pulse. So, the reflected wave have the same speed as the incident. Yes, sir. Second point, incident wave, reflected wave and transmitted wave, all three have the same frequency. So, sir, the first point and second point are same in both the cases. Now, let's talk about third point. When reflected from a rarer medium, there is no phase change. In the last case, when reflected from a denser medium, what went as a crest came back as a trough. This time, what went as a crest came back as a crest. So this is the point of difference between the wave moving from rarer to denser or the wave moving from denser to rarer. The fourth point, transmitted pulse is in the same phase as the incident. That's same for both of them. So now let's take all the points and learn them together in one go. So important points about reflection and transmission of wave when the wave reaches the interface. The first point, incident pulse, reflected pulse and transmitted pulse. All three have the same frequency in both the cases. Whether the wave is trying to move from rarer to denser or denser to rarer, the incident pulse, the reflected pulse and the transmitted pulse, all three have the same frequency. The second point, the incident and reflected pulse have the same speed. Why? Because they are in same medium. The speed of a wave in a medium depends upon medium. Since the incident pulse and reflected pulse are in the same medium, they need to have the same speed. So they have the same speed and hence they have the same frequency. Now from V equals to F lambda, if the incident pulse and reflected pulse have the same speed, they have the same frequency, they are also bound to have the same wavelength. So remember that I ask this to students all the time. If a wave is incident, some parts get reflected and some part transmitted. Which one will have higher wavelength, the incident or the reflected? Students think something that some part of the energy gets lost, so here the wavelength should decrease. That is not at all the case. Since the reflected pulse is in the same medium, it has the same speed. Since incident, reflected and transmitted, all three have got the same frequency. So reflected and incident have same frequency. So from V equals to F lambda, as incident and reflected have the same speed, they have the same frequency, they are also bound to have the same wavelength. Hence the same wavelength. The next point, the reflected pulse has a lower energy as some part of the energy is transmitted. Hence, the reflected pulse has a lower amplitude. So when the wave, let's say, goes from rarer to denser, some part of the energy is transmitted while some part of the energy is reflected. Now, since the reflected pulse has got lesser energy than the incident one, but it has the same speed, it has the same frequency, it has the same wavelength, what changes actually is the amplitude. If the incident pulse has an amplitude A1 and the reflected pulse has an amplitude A2, since some part of the energy has been transmitted, the reflected amplitude must be less than the incident amplitude. So A2 has to be less than A1. So this is the meaning of third point. The fourth point you should know. When reflected from a denser medium, it means that the wave is originally moving in rarer medium and it is trying to enter into denser medium. So when reflected from a denser medium, the wave undergoes a phase change of pi. That is, a crest reflect back as a trough. So what goes as a peak, that thing gets reflected back as a trough when reflected from a denser medium. Next point, when reflected from a rarer medium, there is no phase change. So what goes as a crest come back as a crest given that it is reflected from a rarer medium. So a crest reflect back as a crest. And the last point here, the transmitted pulse is in the same phase as the incident pulse. So whether the wave is trying to move from rarer to denser or from denser to rarer, the transmitted pulse has the same phase as the incident. So what goes as a crest is transmitted as a crest irrespective of the wave is trying to move from rarer to denser or from denser to rarer. Let's continue and let's talk about standing wave now. So what is a standing wave? A wave which is standing. So how can a wave stand? A wave should continuously move. Actually, the wave continuously moves. But if two identical waves of same amplitude move in opposite direction, it appears as if there is no energy change in a small given part. So it appears as if we are looking at a standing wave. So how are standing waves formed? When two waves of same amplitude, same energy, moving in opposite direction, superimpose, they form standing wave pattern. Once more, when two waves of same amplitude, moving in opposite direction, superimpose, they form a standing wave pattern. So let's assume two waves of same amplitude moving in opposite direction. Let's say the equation of first one is given by y1 equals to a sine omega t minus kx. Just by looking at the coefficients of t and x, you can see, okay, they have got opposite sign. This wave must be moving in the positive x direction. Similarly, think of another wave of same amplitude moving in the negative x direction. So y2 equals to a sine omega t plus kx. Here they have got opposite sign, so this moves in positive x. Here they have got same sign, so this wave moves in negative x. Now when two waves of same amplitude moving in opposite direction superimpose, what they give rise to is called a standing wave pattern. How? Let's see. Now you will say when these two are superimposed, the resultant displacement at any point in y direction, which will be equal to the displacement in y direction due to the first wave plus the displacement in y direction due to the second wave. So you will say y resultant has to be equals to y1 plus y2. y1 is given by a sine omega t minus kx, y2 is given by a sine omega t plus kx. Now bachon, from the formula of sine of a minus b, you can write sine a minus b as sine a cos b minus cos a sine b. And one can write sine of a plus b as sine a cos b plus cos a sine b. So sine omega t minus kx can be written as sine omega t cos kx minus cos omega t sine kx. Similarly, sine of omega t plus kx can be written as sine omega t cos kx plus cos omega t sin kx. Okay, so substitute them. So here you will get a times sine omega t cos kx minus a times cos omega t sin kx, expanding here sine omega t minus kx. And by expanding sine omega t plus kx, you again get two terms, a sine omega t cos kx plus a cos omega t sin kx. So now from here you can see that this term minus a cos omega t sin kx and plus a cos omega t sin kx gets cancelled. So what you are left with is a sin omega t cos kx plus a sin omega t cos kx. That gives you 2a sin omega t cos kx. Now you can take this sin omega t part to the side and you will write it as the resultant y equals to 2a cos kx, 2a cos kx times sin omega t. Sir, why you have written this in this particular fashion? Now what I am going to say is the most important thing you should understand for standing waves, and then standing wave will be super easy. Just understand that any particle on the string having an x coordinate x, any particle on the string having an x coordinate x oscillates with an amplitude 2a cos kx. If I write y equals to a sine omega t, this is what? So this is equation of SHM of what? A particle oscillating in the y direction. What is a? Its amplitude. What is omega? Its angular frequency. Now visualize that. What does this particular equation tries to tell us? This equation says that there are different points on the strings, yes, and all different points have got different x coordinates, yes. Any particle having x coordinate x oscillates in y direction with an amplitude equals to 2a cos kx. And all the particles oscillate with same angular frequency omega. So all the particles on the string oscillate with the same time period, but different particles on the string have got different amplitude of vibration. And any particle having x coordinate x oscillates with an amplitude equals to 2a cos kx. So a point with x coordinate x vibrates with an amplitude 2a cos kx and with angular frequency omega. So different particle on the string which have got different x coordinates, they have got different amplitude of vibration, but all of them vibrate with the same angular frequency. Now if you have understood this particular statement, let's move on and understand standing waves in greater detail. We know that the equation of standing wave is given by y equals to 2a cos kx sin omega t. Yes, sir. Any particle having a x coordinate x will oscillate with an amplitude equals to 2a cos kx. So a particle having x coordinate x will oscillate with an amplitude 2a cos kx. As you move along the string, the x keeps on increasing. Yes, sir. So the input angle kx keeps on increasing. As the x keeps on changing, kx keeps on changing, hence the value of cos kx keeps on changing. Now, cos kx is a cos function, and cos is a function in which as the angle keeps on changing, its value keeps on changing. Cos 0 is 1, cos 90 is 0, cos 180 is minus 1, cos 270 is 0, cos 360 is 1, right? So as you keep on moving along the string, the x keeps on increasing, so kx keeps on increasing, and the value of cos kx keeps on fluctuating. So different point on the string will oscillate. They all will do SHM in y direction but with different amplitudes. Now there will be some particular points for which amplitude will be 0. Why? Because the value of cos kx will be 0. If the value of cos kx becomes equals to 0, their amplitude will be 0, and if a particle vibrates with 0 amplitude, it means that it is not at all vibrating. It is at rest. Such points are called nodes. So we need to understand what are nodes. Nodes are the position where the particle vibrates with 0 amplitude. Such points are called nodes. To find nodes, the amplitude should be 0. For amplitude to be 0, cos kx has to be 0. And for cos kx to be 0, what has to be the value of kx? Sir, for cos kx to be 0, the input angle kx has to be how much? So sir, cos 90 is 0, and then cos 270 is 0, and then cos 270 plus 180 is 0. Or when you talk in terms of pi, cos pi by 2 is 0, 3 pi by 2 is 0, 5 pi by 2 is 0, 7 pi by 2 is 0, 9 pi by 2 is 0. So for cos kx to be 0, kx has to be equals to pi by 2, 3 pi by 2, 5 pi by 2, and so on. If you want kx to be equals to pi by 2 or kx to be equals to 3 pi by 2, what has to be the value of x? So for kx to be equals to pi by 2, 3 pi by 2, 5 pi by 2, the value of x has to be equals to pi by 2k or 3 pi by 2k or 5 pi by 2k and so on. So as you keep on moving along the string, the x keeps on changing. As the x keeps on changing, kx keeps on changing. As kx keeps on changing, you will find certain points for which kx equals to 0. As cos kx equals to 0, their amplitude of vibration will be 0. So, the position of nodes for this particular equation of standing wave are found at x equals to pi by 2k, 3 pi by 2k, 5 pi by 2k and so on. Now there are certain points which vibrate with maximum possible amplitude. For the particle to vibrate with maximum possible amplitude, this part cos kx should be plus minus 1. So antinodes are position of maximum amplitude where the particle oscillates with the maximum possible amplitude equals to 2a. And for this maximum possible amplitude, the value of cos kx should be plus minus 1. For cos kx, for cos of the angle to be plus minus 1, what has to be the value of kx? So sir, cos 0 is 1, cos 180 is minus 1. So cos pi, cos 0, they have got value of minus 1 and plus 1. So question is, what has to be the value of kx so as to get plus 1 and minus 1? So you will say, sir, the value of kx has to be 0, pi, 2 pi, 3 pi, 5 pi for the value of cos kx to be plus minus 1. So for cos kx to be plus minus 1, which will represent the position of antinode, kx has to be equals to 0, pi, 2 pi, 3 pi and so on. If kx has to be 0, pi, 2 pi, 3 pi and so on, what has to be the x coordinate? So you will say, sir, the x coordinate has to be equals to 0 by k or pi by k or 2 pi by k or 3 pi by k and so on. So visualize these points on a string. So at the x equals to 0, what are you finding? Sir, at x equals to 0, I am getting an antinode. If you keep on moving along the string, the x keeps on increasing, and the first point after the antinode you will find is pi by 2k. Notice that pi by 2k is half of the position of the next antinode. The next antinode will be at pi by k, the next antinode at 2 pi by k, the next antinode at 3 pi by k. And these nodes which are at distance of pi by 2k, half of pi by k, will be present between two consecutive antinodes. So between two consecutive antinodes, you will get nodes, and between two consecutive nodes, you will get an antinode. So visualize this. At x equals to 0, you get an antinode. At x equals to pi by 2k, you get a node, means the point which vibrates with 0 amplitude. At x equals to pi by k, you again get an antinode. At x equals to 3 pi by 2k, you get a node, and so on. Notice that between two antinodes, exactly midway, you get a node, and exactly midway between two nodes, you get an antinode. Now, what will be the separation between two consecutive antinode, two consecutive node, and one antinode and a node? So, see here, separation between two consecutive node and antinode. So, what is the separation between an antinode and a node? So, you will say, sir, this distance has to be nothing but pi by 2k minus 0. When you do pi by 2k minus 0, what you get is pi by 2k. So, that comes out to be pi by 2k. The separation between consecutive node and antinode is pi by 2k. You know that k is nothing but 2 pi by lambda. So if in place of k you substitute 2 pi by lambda, you get pi upon 2 divided by 2 pi by lambda. Here beta pi get cancelled, you get lambda by 4. Similarly, what will be the separation between two consecutive nodes or two consecutive antinodes? If you know that the separation between an antinode and a node is lambda by 4, then the separation between two consecutive nodes or two consecutive antinodes will be double of this. So that has to be equals to lambda by 2. Let's talk more about standing waves. Now, this is not the only possible equation of standing wave. There are other possibilities as well. For example, y equals to 2a cos kx sin omega t, we have learned. For this particular case, we find nodes at x equals to, where kx equals to pi by 2, 3 pi by 2, 5 pi by 2 and so on, because cos kx is 0 when kx is equals to pi by 2, 3 pi by 2 or 5 pi by 2. So you will get nodes at pi by 2k, 3 pi by 2k or 5 pi by 2k. But there are other possibilities of equation of standing waves as well. For example, the equation y equals to 2a sin kx sin omega t also represents the equation of a standing wave. Notice that here again different particles having different x coordinate have got different amplitude, but all of them oscillate with the same angular frequency omega. So now here, tell me, if the equation is 2a sin kx sin omega t, where will you find the nodes? Sir, to find the node, sin kx has to be 0 this time. And for sin kx to be 0, kx has to take which value? Sir, sin 0 is 0, sin 180 is 0, sin 360 is 0 and so on. So kx should be equal to 0, pi, 2 pi, 3 pi and so on. And when I say that kx equals to 0, pi, 2 pi, 3 pi and so on, then I can say that x has to be equals to 0, pi by k, 2 pi by k, 3 pi by k and so on. There are other possibilities as well. The equation y equals to 2a cos kx cos omega t. First I gave sine, this time cos omega t also represents the equation of standing wave. It's just that all the particles having different x coordinate have got different amplitude of vibration and all of them oscillate with the same angular frequency. So each particle is doing SHM. It's just that their amplitude of vibration is different. Now again, for this particular case, to find the nodes, cos kx has to be 0. And for cos kx to be 0, kx has to be equals to pi by 2, 3 pi by 2, 5 pi by 2. So you get the same condition as in the first case. And there are more possibilities. You can even have y equals to 2a sin kx cos omega t. So first I gave sine, this time cos. It's again represents the equation of a standing wave. Now for this time, to find nodes, it will be the same condition as second, as you need sin kx to be equals to 0. So the nodes will be at 0, pi by k, 2 pi by k, 3 pi by k and so on. Now what I want you to do is visualize the standing waves. So now I want you to visualize the standing waves on a string fixed at both ends. Assume that we have got this string fixed at both ends, and let's say the two fixed ends which can't move at all. Why? They are fixed. They are bound to act as nodes. So here you will have two nodes. And let's assume the case when we have one more node exactly midway between these two nodes. So this point won't oscillate at all. It's a node. Now, what does the standing wave pattern looks on this particular string if the string vibrates? I want you to notice this particular motion carefully. Once more, once more, once more. Now, notice that all points start from the same position, okay? The particles on this side, on the left of the node at the center, start moving in upward direction from the mean, while the particles on the right of the node start moving in downward direction from the mean. Yes, sir. And all the particles on the string oscillate with the same amplitude. Just focus on the particles between these two nodes. Okay, the fixed wall and the center node. They move from the mean position together to the extreme position. Each particle have got different amplitude. When they reach the extreme state, each particle has got different amplitude. The particle at the center has got maximum amplitude. That is the one that is antinode. All of them start from the mean together. They reach their positive extreme together. They come back to the mean together, and then they move in the downward direction together. Then they reach their negative extreme together, and then they start moving back towards the mean together, and they have the same time period. All these particles have got different amplitude of vibration, but they have the same time period of oscillation. Why? Because they have the same angular frequency, so they are bound to have the same time period. Moreover, all the particles on two different sides of nodes are out of phase. The particles between the fixed wall and this node start moving up, while the particles between node and this fixed point start moving down. So they have a phase difference of pi. These are starting from mean going towards positive extreme. These are starting from mean going towards negative extreme. So they have a phase difference of pi. So we say that all the points between two nodes vibrate in same phase. So all these points start from the mean, they go in the same phase. All these points between two nodes start from the mean, they go in the same phase. And the points on different sides of node vibrate out of phase. Out of phase means these particles start from mean and they start going towards positive extreme. So their initial phase angle is 0. All these particles start from mean and start going towards negative extreme. So their initial phase angle is pi. So all the points between two nodes, all these points are in same phase, and the points on different side of nodes, this point and this point, they are out of phase. They all have the same time period. We will talk more about standing wave on strings and organ pipe, Doppler and beats in the next hour. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.